Okay, so today we're going to talk about the conditional statement. The conditional is just if-then. So recall that we discussed one example of this, and I gave you the notation, but then we sort of left it alone for a little bit. It's slightly more complicated, and we're going to deal with it right now. So in English, what's an if-then statement? If it rains, then I will bring my umbrella. There's an example. If there is a transit strike, then I won't give a final.
Really? How there is?
Okay. So this actually happened. There was one year there was a transit strike. So according to this statement, what happened? I didn't give a final. Okay. So that's part of what an if-then statement means. Now, what if there was no transit strike and I don't give a final? Am I a liar?
Yes.
No, why not?
Because there wasn't a transit strike. So
Right. Exactly. The statement, if there is a transit strike, then I won't give a final, only covers the case of there being a transit strike. So if there's no transit strike, basically, this conditional statement doesn't apply, therefore it's true. Or there's, if you like, there's no way to make it false. Right? Because I'm only hooked into a promise if what? If there's a transit strike. No transit strike, then basically I haven't said anything that you can apply. Okay. So if there's no transit strike, but I do give a final, am I a liar?
yes. Wait, no, you're not. Hold on. Huh?
If there's no transit strike and I give a final. No, still consistent. What if there's a transit strike and I give a final? Now I'm a liar, exactly. Okay, so notice that this is the only way to make a conditional false. Well, here we go. So let me remind you of the notation. It's P arrow Q, and we say if P then Q. So in this last example, what is the statement P?
If it rains.
No if.
That's there is transit.
P is there is a transit strike.
Oh.
What is Q?
If it rains, no final. What?
I
the
guess.
second one.
Yeah, then right. I won't give a final. Right. Or there is no final. Okay. So again, so now let's make a truth table for this. Which part? Okay. So diagramming the last sentence, it's if P then Q. Remember, P and Q are variables that represent simple statements. If then is a compound statement made up of all these little bits. Okay. Does that make sense? Okay. So what does the truth table for if P then Q look like? Well, we just said it. It's only false when we have what?
When Q is false. When Q is wait.
Right. Is there a requirement on P?
No.
Look at all our examples. What's the only way for the conditional is an if-then statement. What's the only way for the if-then statement to be false?
Oh,
If
if
P is true and Q is false.
If P is true and Q is false. Because once P is true, that hooks me into my promise, so I have to deliver. But if Q is false, that means I didn't deliver. Does that make sense? If P is false, there's no promise. Promise doesn't go into effect. Does that make sense?
Yeah.
Okay. So, long story short, everything else is true. P, Q, okay. So we have true, 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 false, false, true, false, false. So true then, if true then false is false. Because that means there was a promise and it was broken. Everything else is true. So here's another example, here's another way to think of it. If the Colts win, I'll pay you $5. You're only on the hook if the Colts win. If they lose, I can do whatever I want. Give you $5, not give you $5. Watch the next game, doesn't matter. Okay. So in other words, the conditional is false in only one case. What other statement that we know is false in only one case? We only know a couple different kinds of statements or connectives. One of them is true 3 times but false once.
P and Q times false. P and Q was false.
What is? And is false 3 times. And is true when? And is true when they're both true. So what's false? What's true 3 times but false on only one? 4. Exactly. So what we're going to do right now is we're going to set up an equivalence between an if-then statement and an or statement. Okay. Sorry, one sec. But how to do this is not immediately obvious, because when is an or statement false? When both of them are false. But is that the case with an if-then statement? No. So we've got to fiddle with. So it may not immediately seem like we can make an equivalence between the two, but we can fiddle with it a little bit so that they are true and false, so that they are false in exactly the same case. So how do we do that? Or is false when you have false false. If then is false when you have true false. So how can we manipulate this around so that they happen in exactly the same circumstance? Yes, but it's or. So that's exactly it. That was very quick and very clever. The way to do it is to say not P or Q. Because what we want to do is we want to switch around the value of P. So what switches around the value of P? 9. Very good. That's actually the quickest anyone's ever gotten it. There you go. So we very cleverly have an equivalence. Not P or Q is the same as if P then Q. Because they're true and false in exactly the same way. So let's think about this in terms of words. Our last, the Colts question, if the Colts win, I'll pay you $5. Turn this into the equivalent or statement. Well, if the Colts win, I'll pay you $5. What's P? Not if. The Colts win. Remember, it's if P then Q. So P is the Colts win. What's Q? I pay you $5. So that's P and Q. Now, so what if we want to turn this into an equivalent? We want to turn this into not P or Q. So now turn that round into English. The Colts don't win, or I pay you $5. And if you think about it, it should be clear why these things are equivalent. Remember, if the Colts don't win, then I'm off the hook. So the only other case means I'm going to have to pay you $5. So we have an equivalence. Next. What is the negation of the conditional? And again, remember, conditional just means an if-then statement. Well, the way we're going to get to the negation of the conditional is we know what an if-then statement is equal to. What's it equal to? It's equal to this certain or statement. Do we know how to take the negation of an or statement? Yes, we talked about that last time. So that's all we're going to do. So, whoa, I've given everything away. Okay. So, not if P then Q. Well, we know that P then Q is equal to not. Is equal to not. If P then Q is equal to not P or Q, so taking the negation of the if then statement is the same as taking the negation of this. Now, what is the negation of an or statement? It's going to be an and statement. And exactly, you negate both of them. So you get what and what. And that's exactly it. Exactly, that's exactly when it's a lie. Colts win and I don't give you $5. Okay. Now also, when you did this conversion, you actually did something clever automatically. Because technically speaking, what is the negation of not P? Technically speaking, it's not P. But that's just equal to P. We sort of, in English, we know this so automatically that you don't even realize you're doing the conversion, but this is true. In math, we would say negative 3 is the same as 3. And you actually need to think about that for 2 seconds and maybe prove it. But to us, it's so intuitive that we just do it automatically. But it's true, so it's okay. Alright, so now I'll give, let's see. Let us make a truth table for this fancy thing. Let me pop this out of the way. Okay. So let's sort of work it through together. What columns do we have? Definitely got PQ. What else? We're going to need not Q. Who what?
P then not Q.
Right. We'll need if P, then not Q. And what else do we need? And then the whole thing, right? Because then we have all the pieces. Okay. And how many rows are we going to have? How many variables do we have? What are the variables? P and Q, 2 variables, so how many rows? 4 rows. Okay, so the first row is going to be what? It's going to be true, true, and then true, false, and then false, true, and then false, false. Okay. So let's step through it. So in the first row, what is not Q? False. And then what is if P, then not Q? What are the values? If true, then false. So what is that? Yeah, that's the one case where it's false. Okay. So then what about the last bit? The whole statement. Because what values do we have? Check it. You've got false or false, which gives you false. Remember, that's the whole point of making all the columns in the truth table, is that, for example, when you get to the final statement, what are you looking at? You're looking at, I've got this thing or this thing. But the whole point is that we already know the values of those two things, because that was what we wrote down in the truth table. What's the value of the first thing? False. What's the value of the second thing? False. So it's false or false. So that gives you false. So again, remember, that's the whole point of doing a truth table. Exactly. So you don't have to process it all at once. You already have the values figured out. Okay, moving on. Next row, not Q, is who did that? Okay. If P, then not Q. Well, what are the values? Right. It's if true, then true. That's also clever. So it's true. And then what's the last piece? Well, what are the values that we're working with?
True or true.
True or true. Therefore,
True.
so it's true. Okay. Not Q
False.
is false. If P, then not Q.
False.
It's if false, then false.
False. True. Oh yeah, it's true.
It's true.
Oh, no.
Oh, I haven't
Then our last statement is true or false, which is, and then last row, not Q is true. If P, then not Q is if false, then true. What's that? That's true. And then our last bit is true or true. So it's true. Okay, so 2 comments on this. First of all, by the time you get to when you get to any column, you're not figuring it out from scratch. You should say, for example, how do you figure out this one? You say, well, it's true or true. And what's that? That's true. So that's how you should be thinking of this in your head. That's the first thing. The second thing is, as Daniela commented, we've been doing everything so far row by row, but sometimes you can save yourself some mental effort if you go by column. So, notice what Daniela said. Look at the if P then not Q column. The first entry was a false. But what do we know about an if then statement? There's only one case where it's false. So if that's the case where it's false, then what do we know? Everything else is true. So you can immediately fill in the other 3. Uh-huh.
The false be false, then the, I think it's the third way down.
Uh-huh.
Why is P why is P not Q?
In the third one. Because this is if false, then false. Right. No, because if false, then false. Remember, the only time when is a conditional is only true if I'm on the hook for my promise and then I break it. But if the if false part says I'm not on the hook for my promise, so that means I don't have to do anything. So that means it doesn't matter. Does that make sense?
Yeah.
Okay. Right. So that's understanding the Zen of the conditional. All right. Okay, so let me write down that bit. Okay. So note that. All the other. Okay. So there's that clever observation. Okay. So another observation, which is sort of philosophical, saying P is true is sort of like saying P. sort of like you're asserting it. Q is false is the same as simply saying not Q. Because it's like you're asserting not Q. So when you just write down P, that's like saying it's true. And think about why this makes sense in English. Think back to the previous problem with the Colts. The original thing was, if the Colts win, then I pay you $5. Well, just writing P, what is that the same as writing down in English? The Colts win. So it's like writing down an assertion of something that's true. Does that make sense? If you just say the Colts win, it's like you're saying something is true. I just said the Colts win. So I guess Colts win. So this is going to come up a little bit later when we talk about these more complicated arguments, which we'll be getting to, I think, next time. Okay. All right. So those are the basics of the conditional statement, which is the if-then statement. I want to talk a little bit more about other versions. Some ways a little fancy, a little tricky. Okay. So again, let's go back to my original example. If there is a transit strike, then you go home, or in other words, then there's no final. Okay. From this, there is something called the converse. Actually, oh, I know why. I just realized why I did that. Okay. All right. So I'm saying go home is the same as saying there's no final. But okay. So if there's a transit strike, then you go home. The converse is if you go home, then there's a transit strike. And this is if Q then P. So based on the original statement, this is the converse. If your original statement is if P then Q, the converse is if Q then P. And there's also something called the inverse. So if the original statement is if P then Q, the inverse is not if not P, then not Q. If there is no transit strike, then you don't go home. And you have to take a final. Then there's also something fancy called the contrapositive. So if the original statement is if P then Q, then the contrapositive is if not Q, then not P. Now what would that be in English? If you don't go home, then there is no transit strike. Again, if you don't go home, it means you have to take a final.
Does that have to do with the English?
That's actually exactly what we're going to figure out right now. Is which of these are the same? Now obviously if you just go directly in terms of literally letter by letter when you write it down, all these four are different. But the question is, are any of them equivalent? Do any of them mean the same thing? I think that's what you're asking.
Yeah.
Yes. So the question is, do any of these mean the same thing? So let's check it out.
What is the English and contrapositive?
Okay. Okay. So actually, so let's get some ideas. So Stephanie Stephanie said that the inverse and the contrapositive are the same thing, are equivalent. Okay. So if there's no transit strike, then you don't go home. Is that equivalent to if you don't go home, then there is no transit strike?
Yeah, it's the same because you're not, if you don't go home, go home.
Okay.
It's just, yeah.
Okay. So then, similarly, because having the same relationship is the first two, the original statement and the converse. If there's a transit strike, then you go home, you would say is the same as or is equivalent to if you go home, then there's a transit strike. So are those the same? Are you also arguing that those are the same? Equivalent.
Which one?
The first two. The original statement and its converse. If there's a transit strike, then you go home with no final. If you go home with no final, then there's a transit strike. Can you go home with no final? I'm sorry, with or without? Without a transit strike. Good question.
No, because you only go home if there's a transit strike.
Is that true? Do you only go home with no final if there's a transit strike? If there is it possible, according to the original statement we're saying? Which statement are we using? The original statement? According to the original? According to the original statement, can there be no transit strike, but I send you home with no final?
Yeah.
Sure.
Yes.
That's the entire thing that we were just talking about. I'm only locked in if what happens? If there's a transit strike. If there's no transit strike, what do I have to do? According to the original, again, right now we're looking at the original statements.
If the final is transit
If
strike.
there is a transit strike, then you have to not go with the final.
Exactly. There's a transit strike, I'm locked in to sending you home with no final. What if there's no transit strike?
You don't have to send the final.
Absolutely not. Absolutely not. That's not what this says. Yes.
So
This is a common misunderstanding of the if-then statement.
So you don't have to give up the final if there is no transit strike.
If there is no transit strike,
then
Then obligated
you don't have to do it.
then I can do whatever.
Yeah, but if you're assuming that if you're saying that if you're going to send this home, if there is one, then you assume that if there isn't one, then you take it.
Absolutely not. That's not what this is saying.
So the way it seems like there is a strike, then you're gonna go home.
It would seem to be implied by this statement, but it is absolutely not implied. This is only a promise about what will happen in the case of a transit strike. This says nothing about what will happen if there is no transit strike. Now, this is one of the reasons why there is some confusion, is that often when we're saying this in English, we also mean that if there's no transit strike, then I do give you a final. But that's a different statement. In logic, that's a different statement. That is not included in this statement in logic. So in logic, the if-then statement, the way to think about it is it only covers the case where, I guess, the first half of our promise comes true. First half of our promise isn't true, then we're off the hook. We can do whatever we want. Okay. Okay. Here's another way to. I'll go back to the original. I'll go back to one of my first examples. If it's raining, then I'm going to bring my umbrella with me. What if it's not raining?
You can still bring an umbrella.
I can still bring an umbrella with me if I want. Just in case, if you like. Okay, does that make sense? If it's raining, I bring an umbrella. That's the statement. So then what if it's not raining? Really?
You can still bring it.
Really?
I brought an umbrella today. I brought an umbrella today, so I mean it's true.
If it's really, really cloudy,
I don't see the point in saying that I don't see the point in saying it if you might bring it anyway.
exactly. This locks you into something if the precedent antecedent. I'm going to avoid using that technical language. If the first thing happens, then you're locked into doing the second thing. It doesn't cover other cases. Okay. Here's Here's another one. If it's let's see. If it's a Monday, we have this class. Is that true? Yeah. What if it's right? If it's a Monday schedule, we have this class. Okay. This is when everyone's inner lawyer comes out. Okay. So, if it's a Monday schedule, we have this class. Now, what if it's not a Monday schedule?
We can still have this class.
Exactly. Now have I convinced you? Yeah. Okay.
So you're saying like two, less than two is the same thing like not two or two?
Yes, that's true.
So you could get replaces.
Yeah, okay. You're exactly right. One way to do this would be to literally write it down and figure it out. Right. You're right, and in fact, there's something that people do when they develop this logic theory more fully. Is you actually, as Rian actually pointed out, you actually don't need if-then statements to make logic theory, because you can just replace it with an or statement. You're exactly right, and in some logic systems they just do that, just so there are no conditionals. So, what the heck? Let's do it, right? So, if P then Q is the same as not P or Q. What about the? Let's get rid of this. Okay. What about if Q then P? What is that the same as? Okay. And now you can see those aren't the same. Okay. What about the inverse? P or I don't know. Do you negate the second one? No. It's the negation of the first or the second. Now, in this case, what's the negation of the first? P. And then what's the second? Not Q. So you get P or not Q. And then what about for the contrapositive? Okay. So now you tell me which ones are equivalent. I know, Rian, this is your idea. You said this would make it easier. Let's check it. The original statement is not P or Q. Where else do you see that? Yep. There you go. Because not P or Q is the same as what? Q or not P. So there you go. In an and, you could still switch them also. true or false is the same as false or true. True and false is the same as false and true. So you can with an or and you can switch them.
So then the inverse and converse will be the same.
And the inverse and the converse are the same. Absolutely. Okay. Now this doesn't give us any insight into why this is true, but now we certainly know which ones are equivalent. Okay. So let's see. All right. So we've done an in-depth discussion as to whether or not, let's see, the original statement is the same as its converse. Stephanie, that's what you made us talk about, and we see that that's not true. Similarly, a lot of people say if there's a transit strike, then you go home is the same as if there is no transit strike, then you don't go home. But again, we can see that that is not true. It may be true when we speak in English. It may be what we mean, but it's not true in logic. So originally I was going to draw a truth table, but I think through our discussion and through writing it out symbolically using ors, we can see it directly. So I'm just going to skip that. Okay. Now, saying the original statement is equivalent to its inverse happens a lot. It happens so often that misunderstanding gets its own name. It's called the fallacy of the inverse. Okay. So again, even though the inverse sounds like it should be right, it's not for everything that we talked about. Okay. Similarly, the fallacy of the converse also happens. It's a mistake that happens so often it also gets its own name, assuming that the converse is the same, is equivalent to the original statement. Okay. And here's a really good example of why the converse isn't true. If I own a Mac, then I own a computer. Is that true? Okay. Unless you know a Mac I don't know about. Okay. If I own a Mac, then I own a computer. Okay, good. What's the converse? That's actually the contrapositive. Okay. So the converse is if I own a computer, then I own a Mac. How do we feel about that statement?
Not true.
Not so much.
Because you have computers that are not Macs.
Exactly.
That Macs are computers.
Exactly. So if I own a Mac, then I own a computer. We agree that in the real world that's true. If I own a computer, then I own a Mac. In the real world, this isn't necessarily true. It might be true, it might be false, depending on what the computer is. So do you now see why, for example, this one doesn't work?
Yeah, I get
Okay. This one, okay, right. Okay. Also, what about the inverse? The inverse is if I don't own a Mac, then I don't own a computer. In the real world, is that automatically true? Certainly not. But now, let's look at the contrapositive. The contrapositive says, if I don't own a computer, then I don't own a Mac. Is that true?
Yeah, that's true. Because you don't even have a
Yeah. If you don't have a computer,
How can you have a Mac?
you can't have a Mac. Again, in the real world.
So the contrapositive is
No, no. It's always equivalent to the original statement. So here I'm just giving an example. Obviously, I could make, if it's Tuesday, then I must have a pink hat on. Then it would have different values. I'm just giving an example where you can clearly see that the original statement is the same as flip flip, the contrapositive. So if I own a Mac, then I own a computer is the same as saying if I don't own a computer, then I don't own a Mac. Same thing. So this is a case that shows you clearly the original statement being the same as the contrapositive, whereas the converse and the inverse clearly aren't saying the same thing. So I think that's that for that. Okay, right. Okay, so any questions about these things? Okay. So as you approach these questions about conditionals and if-then, it's important to me. The mental trick that I use is to remember that a conditional is true unless you're on the hook for the promise and you don't follow through. In other words, if true, then false. Otherwise, it's okay. So that's what helps me think about the if-then statements. And then what we just talked about here with the converse, the inverse, and the contrapositive, we're going to get into logical arguments a little bit more, and we'll be using this a lot more. But remember, try to think through our discussion of the past, 20, 30 minutes, about how the original statement is the same as the contrapositive. But the converse and the inverse are saying something different. Which, again, because of how we speak in English and our intentions in English, it doesn't exactly line up. But again, with these couple examples that we talked about, it should start to be clear that we're talking about different things. Okay. Question? No, it's good? Okay. All right. Okay. So an application of this logic stuff. Actually, before I talk about this one, I just want to mention that all of this logic stuff, before I mentioned inner lawyer coming out, there is, if you intend to become a lawyer and go to law school, as you guys may or may not know, you have to take an exam called the LSATs. Okay, so some people have heard of this. So there is an entire section of the LSATs that is just dealing with logic. Yeah, okay. Now it doesn't look like if P then Q. What it looks like is logical arguments, and those sorts of arguments we're going to be getting to over the next class or two. But this whole, as you can imagine, dealing with the law has to deal with thinking about things in a very precise way, when something implies something else as opposed to when it doesn't. So this is an important skill that lawyers should have, and they should be able to construct arguments, and also, when presented with an argument, they should be able to poke holes in it, as Dustin did earlier. There you go. Okay. Okay. So that's one interesting application that we're actually going to get into a bit more coming up. Another interesting application, can you believe, is circuits. Circuits. Can you believe it? I know. What could circuits possibly have to do with logic? Let's check it out. Oh. Or that. Okay. Well, here's the immediate connection. A circuit being on or off, you can match that up with saying a statement is true or false. So statement is true is the same as circuit is on or light bulb is on, if you like. Well, that sounds very clever, but how does, for example, P or not Q, how does that look like a circuit? Well, that's what we're about to talk about right now. Yep. Okay. 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 So what does it mean? So in these pictures, what does it mean? What does it mean for a circuit to be on? It means that the current can get from start to finish. Imagine that there's a power. If you like, imagine that there's a power source on a light bulb. Okay. I wish. Okay. Okay. So, I'm going to show you the basic idea. So, here is a circuit. Okay. So, on the left side, what we have is a circuit. This represents the statement P. Now, what would it take for this circuit to be on? You'd have to close the switch. So, closing the switch is exactly the same as saying at what in logic?
That P is true.
That P is true. And opening the circuit would be the same as saying what in logic? That P is false. So this is the basic idea for connecting circuits and logic. Does this make sense? Okay. So what does it mean for the circuit? So what we're saying for what it means the circuit to be on is that, say, on the left side you have a power source and on the right side you have a light bulb. So when can the current get to the light bulb? When, sorry? Power source always on. In the first case, can the current get to the light bulb?
Yes. Because it's open.
Okay, in order for current to travel through a wire, there needs to be a wire there. Right, so in the first case, is it connected and can the current travel through it? What about in the second case? That's it. Okay. So this is the basic idea. So what we're going to do now is we're going to build up more complicated statements. So what about this? We've got basically one wire, and on that wire we've got a P switch and a Q switch. Now, in order for the circuit to be on, what would we need to be the case?
P and Q both have to be closed.
Both switches have to be closed. That's the same as. So that's the same as what statement? P and Q. It's just the same as P and Q. Because in order for the circuit to be on, you need P to be closed and you need Q to be closed. That's the same as saying what in logic? P is true and Q is true. Just like P and Q. You dig? Okay. Let's take a look at this one. What logic statement does this circuit represent?
P or Q.
How come?
Because either one could make the circuit close.
Exactly. You only need one of them to be closed in order for the current to get through. Just like an or statement. So that was the first one I had you guys do directly. Does this make sense? Okay, so let's talk this one through. In order for current to get from one side to the other, what has to be the case with these switches? Which ones have to be closed? Right. So either P has to be, if P is closed, then you already have a circuit. If Q is closed, then you have a circuit. And of course, if both are closed, you still have a circuit as well. And that's the same as saying, if you put it in logic, it's true when P is true or Q is true. That's simply the same as saying P or Q. That's how we go from circuitry to logic. Fancy one. What is this the same as?
Or
P or Q and R.
Right. So overall, what kind of logic statement is this circuit? This is an OR circuit. Now it's an OR circuit between two statements. What is the first statement?
P is on.
P. And then what is the other statement?
Q and R.
It's Q and R, because for the other one you need both of them to be connected.
Isn't it?
Yep. So in the same way that with the truth tables, you had to take the entire statement and break it down into its individual components, you're doing a similar sort of thing with the circuits. You have to understand the individual components and how they build up. In this case, it's understanding that when you have two switches in a row, what kind of statement is that?
And.
That's an AND statement. And when you have, how shall I say this, a loop with switches on opposite sides, what kind of statement is that?
Or.
That's an OR. Okay. Now, by the way, I've avoided using the actual the physics electricity names for these things. When two switches are in a row, as in the AND statement, that's actually called a serial circuit. And when you have the OR statement with them on the loop, that's called a parallel circuit. Whoa. Okay.
P or not P and then R.
Right.
Or Q and not R.
Right. So, at its overall, what kind of logic statement is this circuit?
Or.
It's an OR.
And or. Or and or. And or.
It's two ORs.
Okay.
I've got something or something or something or something. Now, what is the first thing?
P.
The first thing is P. What's the second thing?
Not P and R.
Not P and R.
Or Q and not R.
And then the last one is Q. Is Q and not R. Okay. So that was the tricky one. Yeah. Okay. Okay. So this is really sort of like the hardest one with all these different components running around. If you can understand this last one, that pretty much means you can understand this.
I think it's easier than it's easier than when we first started. But this way, like, why didn't you show us this way at the beginning?
It's that's well, okay. I'm glad it all makes sense now. Okay, great. Okay, so yeah, Marcelo.
Can you go back and tell me first?
The which one?
The whole.
This example from the beginning?
Yes.
Okay. So the first thing to do is to look at the circuit and to assess its overall structure. So overall, what do you have? You've got an OR circuit. Because in order to get from the beginning to the end, how can you get there? You can get there either on the top branch, or on the middle branch, or on the bottom branch. So overall, this is an OR with 3 branches. So again, we know we've got something or something or something. What's the first branch of the OR? Just P. So that's the P. What's the next branch of the OR? Right. So we've got a not P, then an R. But how are these guys connected? It's an AND because clearly to go through the middle branch, you need both of them. So the middle branch is not P and R.
So like.
And then the third branch, Q and not R. So overall you have P or not P and R, or Q and not R. And that's the logic of this circuit.
So like the AND has to be at that level, kind of like 2.
Right. Right. Okay. So now is that straight? Okay. Sorry? Yeah, I can make up an example where you have that sort of thing. Okay. So I'm going to make up a fancy AND circuit. So you could have
It's still on the same line.
okay, now I've got to label these things. Let's call this P. Okay. So there's your big fancy circuit. And the question is, what is this the same as? There we go. Okay. So overall, what kind of circuit is this? Nope. Overall, what kind of circuit is this? This is an AND circuit.
It could be P and R and no, it could be P and R or R.
Okay. In this AND circuit, what is the first piece?
P or R.
It's P or R.
And not P or
P or R. That's the first piece. Now, this. What about the second piece?
Not P and Q.
Not P and Q, or P and R. And let me put in parentheses so it's clear. Exactly. So overall, this is an AND circuit. However, in the second half of it, it's complicated. There's an or statement in there. And then, of course, within each or statement, there's an and in there. So it's very nested. But that's why, again, you have to go piece by piece and layer by layer. So, Juan, to answer your question. Okay. All right. So, is that straight? Okay.